Right. So, now let us turn to the problem of planetary motion as encapsulated in Kepler's laws of planetary motion. As you are aware, there are 3 such laws, and what I am going to try to do here is not to derive these laws or anything like that, but merely to take these laws and put them in the broader perspective of understanding the two-body central force problem itself, and point out what is common between the general problem and the particular problem of Kepler's of planetary motion and what is not. So, let us start by saying that we have a particle of mass little m. Instead of mu, I might as well use little m, and we write down its equation of motion, which is m times dr over dt equal to its momentum p, and the rate of change of momentum is given by the force on the particle by Newton's second law of motion, which in this case is capital G, the mass of the sun, the center, whatever is attracting it, times the mass of the planet, divided by r squared times E sub r. Now, let me simplify this a little bit by writing this as equal to minus some constant capital K over r squared E sub r. So, this here is some positive constant whose value is going to depend on the particular units that you use, the particular masses, and so on and so forth. So, this is the problem that one has to solve. These are 2 coupled equations for the vectors r and p, and the statement is given r of 0 and p of 0, one should be able to deduce what r of t and p of t is by solving these 2 coupled differential equations. But because there is r dependence sitting here, this problem is not trivial at all, and this is what Newton addressed. After seeing a lot of data from Kepler, who then enunciated his laws empirically, Newton derived those laws completely from the fact that he could write down the equations of motion and solve this problem in some sense. Today we would not solve these equations the way Newton tried to solve them, by the very specific geometrical tricks that he used and so on. We just use the calculus and our knowledge of differential equations to try to solve these particular equations. But the interesting thing is the interpretation of the solution more than anything else, and we know that the solution to this is that when you have an attractive potential, a 1 over r potential, there are bound states possible, which are orbits, which are ellipses, and so on and so forth. Now, where does this take us? What does it tell us? Well, the first law says that this mass m, now let me do it in an abstract form, moves in an ellipse for any initial conditions. It moves in an ellipse with the sun at one of the foci. So, there are 2 foci and the center of attraction is here. So, that is the origin. So, already you can see that even though this problem looks completely spherically symmetrical, the solution does not have that symmetry. The solution has an eccentricity. It is an ellipse. It is not a circle. Circular orbits are a special case of elliptic orbits. However, in this particular instance, it turns out the planets have elliptic orbits with undoubtedly small eccentricities as it happens, but nevertheless they are ellipses. And in principle, the eccentricity could be arbitrary. After all, we do know of comets which have highly eccentric elliptic orbits. We know of artificial satellites which have extremely eccentric orbits, a very large semi-major axis, a very small semi-minor axis, and yet it is in a stable orbit around the Earth. So, in exactly the same way, you have ellipses, elliptic orbits with the sun, or rather the center of attraction or origin of coordinates in this case, at one of the foci. So, that is the first statement here. Now, what I would like to ask is there any other potential, any other form of this potential? Instead of this, we have something else, some other force law. Would that also lead to elliptic orbits? Even if we say it is a central potential also, would it lead to elliptic orbits? And the answer turns out to be yes. I will come back to this and point out there is one other central force in 3 dimensions for which you have elliptic orbits possible, but with a slight difference from what this law says. We will come to that subsequently. So that is what the first law said. The second law said something more general. But before that, let me point out here that this particular statement, elliptic orbits with the center of attraction at one of the foci for the bound orbits, is specific to the 1 over r potential or the inverse square law force. So let me write that down, that this first law is specific to the inverse square force law. If it is not the inverse square force law, this is not true. You do not have elliptic orbits with the center of attraction at one of the foci. Okay. To cut a long story short, there is another potential which we will talk about towards the end, where you again have elliptic orbits possible, but in that case the center of attraction is at the center of the ellipse and not at one of the foci. So this is what distinguishes motion under that potential from motion under a 1 over r squared force or a 1 over r potential, the Kepler problem or the Coulomb potential here. The second law says the radius vector from the planet, from the center of attraction to the instantaneous position of the planet, traces out equal areas in equal times. Let us look at this a little carefully. It says that if in an infinitesimal interval of time dt, this is the area traced out, then at a later instant of time, while the radius vector changes, the angular speed changes, everything changes, but this area in the same interval of time dt has got to be equal to that. That is what this says. Now what is this actually telling us? Well, first of all, the moment I say that this orbit is an ellipse, it is clear that the orbit is planar. It is not a 3-dimensional curve, but a planar curve. Why is that? Because it is a central force and there is no net torque on this particle, because notice that the torque on the particle, tau, torque, is equal to r cross f, but f is in the radial direction inwards, and therefore r cross f, the sign of the angle between the direction of the force and the radius vector is 0, and therefore this is equal to 0. And if the torque on the particle is 0, as it is in any central force, it immediately implies, this implies that the orbital angular momentum L equal to r cross p equal to a constant of the motion. Now when the orbital angular momentum is a constant of the motion, this is a vector. Therefore when you say a vector is a constant of the motion, not only is its direction a constant, but its magnitude is also a constant. And what does it mean to say its direction is constant? If the particle is moving in an ellipse in the plane of the blackboard, if instantaneously this is the radius vector in this direction and the momentum at this instant of time is this way, excuse me, r cross p goes into the plane of the blackboard at this point of time, and at a later point of time it should again go into the plane of the blackboard, and at any other later instant it should again go into the plane of the blackboard normal to it, which means that all these little area elements are in the same plane, which is equivalent to saying that the orbit is planar. Okay. So the planarity of the orbit is really arising as a consequence of the fact that the orbital angular momentum is a constant of the motion, both in magnitude as well as direction here. Now the second law says something further. It says equal areal velocities. It says that this little triangle and this triangle have exactly the same area. But what is the actual area of this triangle? If you write it out at any instant of time, if this angle here is delta phi, and this distance is r, then this arc, as you can see, the base of this triangle essentially is arc divided by r equal to delta phi, So it says that this arc or the base is r delta phi. The base of this infinitesimal triangle is r times delta phi. What's the area of the triangle? It half times the base times the height. So this little triangle has an area delta A which is equal to 1/2 the base of the triangle, which is r delta phi, times the height of the triangle, which is essentially r, apart from a factor of 2. It says this. We put that factor in, it's equal to this. The rate of change of this area, the areal velocity, therefore areal I should say areal speed actually, because it's not a vector. The area element is a vector, though we can associate a direction with it. This is equal to 1/2 r squared delta phi over delta t, which is equal to 1/2 r squared the angular speed omega, which is delta phi over delta t. So it's really saying that the angular speed multiplied by the square of the instantaneous radius vector is a constant in time. That's what it's saying. On the other hand, what's the orbital angular momentum? In magnitude, the magnitude of L is equal to the moment of inertia multiplied by the angular speed. And the moment of inertia is m times r squared respect to the origin multiplied by omega. And this is a constant in time. So you have omega r squared is constant in time times m, which is a constant, by the conservation of angular momentum, and the second law says half r squared omega is a constant in time, saying essentially the same thing. So it says while omega may change and while r may change, the combination r squared omega does not change. The product r squared omega doesn't change. Out here r is large, omega is small. At this point r is small and omega is large. It zips through much faster here, much greater change of rate of change of the angle, azimuthal angle. So essentially it says the second law, the fact that this is equal to a constant in time is the same as the conservation of orbital angular momentum. So the point I want to make is that Kepler's second law is not specific to the inverse square law of force. It is in fact a general statement. It says that no torque on this particle in a central force, therefore its orbital angular momentum is a constant of the motion both in direction as well as magnitude, and that's all it's saying. So this law, while it's specific, as I said, to the first law is specific to the inverse square law of force, the second law is true in general, valid for all central potentials. In the Kepler problem itself, it's in fact valid even if the orbit is open. So it is certainly true that if you have a comet in a hyperbolic orbit, so here is the center of attraction and here is the orbit of this comet, even if it's not an elliptic orbit, in equal instants of time, this area would be equal to the area traced out in the same interval of time. So the second law, Kepler's second law, is not specific to planetary motion. It's true for all motion in any central potential whatsoever, and in the case of the inverse square law of force, it's valid whether the orbit is an ellipse or a hyperbola or a parabola. It is still true, even for non-periodic motion such as that of comets. It's still true. This law is still true. Okay. So it's worth appreciating the fact that this law is really a general statement, conservation of angular momentum, and not specifically restricted to elliptic orbits in an inverse square law of force. What about the third law? The third law, once again, is specific to the inverse square law of force, and it says, as you know, the square of the time period t squared is proportional to the cube of the mean distance from the sun, which in this case would be some kind of average over the elliptic orbit. So this is proportional to r cubed, and let's say this is the mean radius. It's not important whether it's the semi-major axis or the semi-minor axis or whatever, it's some mean value. It's a length scale which prescribes the size of the orbit, and that the cube of that is proportional to t squared. So what it's really saying is that the same potential, the same force can now support different orbits. So there's an orbit of this kind with a mean radius with, say, time period t1 and mean radius r1. The statement is that the same potential with different conditions, initial conditions, could also support an orbit of that kind with t2 and r2. And what is being said by this statement, what's meant is that t1 squared over t2 squared is guaranteed to be r1 cubed over r2 cubed. So this is the content of the third law of planetary motion. And where does this come from? Well, elementary derivations for a circular orbit are possible. They are not very difficult. It's fairly easy to show that if you assume the special case of a circular orbit, you can easily prove that with a 1 over r squared force, you are going to have a property precisely of this kind for a circular orbit. For an elliptic orbit, it's a little more complicated to prove, but I'm not going to do that. Instead of proving that, I'm going to show you that this law is really a property of the 1 over r squared force and follows from something called scaling, a scaling relationship. It doesn't prove that the orbits are ellipses, it doesn't prove the first law or anything like that, but it still tells you why you have these particular powers. Why 2 here and why 3 there? Why not something else? And why this relation at all to start with? Okay. So the way to understand that law is in this sense, namely, if the potential, if the force exerted by this center of attraction, this inverse square law force, can support a closed orbit, an ellipse, with mean radius r1 and time period t1, it can also support, the same potential can also support another orbit of mean radius r2 and time t2, where the ratio of t1 and t2 is related to the ratio of r1 and r2 in this particular manner. So that's what this law is really saying. And where does it come from? Well, it comes from a little bit of glorified dimensional analysis, nothing more than that, and let me show you how. Let's write the equation of motion in Newton's form for this situation. So you have m times d2r over dt2. This is equal to minus the force, so some constant minus g m1, m2, etc. Whatever it is, we finally cancel out all this and write this as minus k over r squared e subscript r. This fashion. So that's really what the force is. And this is the acceleration. That's some positive constant. Once you give me the masses of the sun and the capital G and little m and so on, this is given to me here. Now I stare at this and I say, well, the dimensions, physical dimensions of these constants is important. This has got dimensions length, this has dimensions time here, this is a unit vector, it has no dimensions at all, this is 1 over length squared, and this takes care of the balance of dimensions in this case here. Now I come along and say that let me change the length scale in the problem by going from r to some r prime. So let's set lambda times r prime. So I don't like the units that I'm using. Instead of choosing the particular units I have, I choose different units so that what I have, a length r, magnitude r, becomes lambda times r prime in this case. No physics should really change once this is done. Well, let's see what the consequence of this is. So this tells me that I have lambda times d2 r prime over dt2 equal to minus k over, and here I have r squared, that's lambda squared r prime squared er. Er or er prime doesn't matter because they are parallel to each other, it's the same unit vector. And it's dimensionless. Magnitude is 1 and its direction is that of the radius vector, which is the same whether you use r or r prime. So this is the new equation, and I bring the lambda to the left hand side, I get lambda cubed times this. The moment I have this, I say, well, if I've changed the scale of length, why not change the scale of time as well? Instead of measuring time in seconds, maybe I measure in minutes or hours or whatever. It should not change any physics. So let me also change variables from t to t prime, which is equal to some mu times t prime. Mu some constant, some number, pure number. Then this equation becomes, in the new variable, I have lambda cubed d2r prime over dt prime 2, and there's a mu squared that sits here equal to minus k over r prime squared er, or r prime, doesn't matter. But that looks exactly like because I pull out a mu squared, because if I differentiate with respect to t, it's like differentiating with respect to t prime with a mu pulled out. Okay. So this says the equation of motion is identical to the old equation. The same physics is going to be described, except that I have this extra multiplicative factor here. So if this factor is set equal to 1, then the physics is unchanged completely, as it should be under this change, redefinition of units or scales of length and time. If you do that, it says lambda cubed over mu squared equal to 1 would imply that, now what is lambda? It's r over r prime. And mu is t over t prime in this case. And what we are saying here is that lambda cubed is equal to mu squared will ensure that this problem, the physics of it, is independent of the choice of scale in length and time. And that implies that if you have two length scales in the problem, r1 and r2, and the ratio is lambda, and you have two time scales in the problem, the ratio is mu t over t prime, then the square of this ratio is equal to the cube of this ratio, which is precisely this law. This doesn't prove that the planets move in ellipses. It doesn't prove that one of the ellipses, the sun is at the center of attraction is at one of the foci. It doesn't do any of that. It says if, all this argument says is, if there is motion supported by this potential, the 1 over r squared potential, with a closed orbit supported by it, with a time scale t1, a time period t1, and a mean radius r1, it also supports, the same potential is also going to support another orbit with time period t2 and mean radius r2, but you're guaranteed that t1 over t2 squared is r1 over r2 cubed here. And this is Kepler's third law. So Kepler's third law is very specific to this force here, because we had to put a lambda squared here to bring that up here, and that's how we got this lambda cubed out here proportional, and then we set it equal to mu squared here. So Kepler's third law, if you like, is a consequence of the scaling properties of this potential, of this force out here. Well, the moment you have that, the natural question to ask is, can I generalize this? Can I have some other potential? Can I have any other potential, and if so, can I find a similar rule? Well, yes, indeed you can. Let's assume, without proving what kind of orbits you have for such potentials, let's suppose that you have a V of r which is proportional to r to the power n. Say. Well, since we've talked about inverse square potentials, let's call it let's leave it as r to the power n. then the force F of r is proportional to the derivative of this potential, so it's proportional to r to the power n minus 1. So what you have in this formula here would be d2r over dt2 is equal to some constant, some other constant, let's call it a, it doesn't matter. If it's attractive, it's got to be this way with a minus sign times r to the n plus 1 n minus 1 times E sub r here. And I do the same trick as before. And then it turns out that lambda times d2r prime over dt prime 2, and again you get a mu squared here because I change from t to mu times t prime. I set t equal to mu times t prime. That is equal to minus a lambda to the n minus 1 is r prime to the n minus 1 e subscript r or r prime, doesn't matter. So this is lambda to the n minus 1, so write it as 1 over lambda to the 1 minus n, and I multiply through here, so you get a 2 minus n. And this says immediately that lambda to the 2 minus n should be equal to mu 2. Therefore, any motion with a characteristic length scale r and a time scale t, if r and t take on values r1 and t1, then that same potential or force will also support a similar motion, open, closed, we don't care, similar motion with time scales t2 and r2, such that the ratio of length scales to the ratio of time scales satisfies this condition here. And in the case of the Kepler problem, the potential was 1 over r, so n was minus 1 and the force was 1 over r squared. So you set n equal to minus 1 here and you get lambda cubed equal to mu squared, leading to this equation here in the Kepler problem. But I mentioned in the beginning that there is one more potential for which this happens. You still get ellipses, etc., and that is the harmonic oscillator potential, which corresponds to putting V of r equal to r squared. So what we have is a particle attached to the origin with a spring, and instead of moving in a line, it moves in three-dimensional space. It's called the isotropic oscillator, and the V of r in that case is equal to 1/2 a spring constant times r squared. So it's like three harmonic oscillators at right angles to each other in the x, y, z directions, and this is the resultant motion. This problem, the potential n equal to 2 in this case, and indeed you discover that in this case there is no dependence on lambda at all of the time scale here. And what is that saying? It's telling us this well-known property which we will come to and prove later, that when you have simple harmonic motion, the time period is independent of the amplitude. In turn, it means the time period is independent of the energy. This property is very, very specific to the harmonic oscillator problem. It's actually one of the defining properties of the oscillator, although it's by no means really unique to the oscillator. There are other cases which are not so simple, where you have exactly the same property, but as far as central potentials are concerned, the only central potential with a power law of this kind, r to the power n for the potential, for which the time period of the motion is independent of the amplitude or the size of the orbit, is the harmonic oscillator potential, n equal to 2. And it also follows as the corresponding equivalent of Kepler's third law, because this thing here becomes lambda to the 0 in the case n equal to 2. That's the only case in which it happens. Let me mention finally that the first law which I said was specific to Kepler's first law, which I said was specific to the 1 over r squared potential, the elliptic orbit part of it is not unique. There is one other central potential for which the orbits are ellipses, the bound orbits are ellipses, and that's this potential. The difference is, in this case, this is the harmonic oscillator. potential. And the difference in this case is that the orbits are ellipses with the center of attraction at the center of the ellipse rather than either of the foci of the ellipse. So in that sense, the r squared potential and the 1 over r potential are different from each other, but the conservation of angular momentum is still true. They are still elliptic orbits with the center at different points, center in one case, focus in the other case. And the third law is different in the two cases. In one case, you have t squared proportional to r cubed. In the other case, you have t squared equal to constant independent of r. So that's the difference between these two potentials. And I thought it should be placed in this perspective.